introduction. So I have a privilege, I had a privilege to witness how Svitlana grew from a young and talented mathematician into a leader in her area, and you will see this from this talk. She started her mathematical career in Kharkov, what is the city in Ukraine, then where she got her master degree. Then she moved to the US, and she worked under supervision of Marius Mitria. So we know around him very well because he was a graduate student at our university, University of South Carolina. So she got her PhD, and that was in harmonic analysis. And then she got her area much broader. For instance, at this point, she is in Minnesota, in Minneapolis, in the University of Minnesota. And now she's the director of Simon's collaboration project, which is like $8 million project, and she's the director. So, Svitlana, you're welcome. So you can podium.
We shouldn't measure mass and money. But anyway, thanks a lot for the. Thanks for a very warm welcome. Huge thanks for the invitation to the organizers of the program. It's a great pleasure to be here. It's my first time in Cambridge, first time in UK actually. It's been very enjoyable so far, and I hope it will be very productive mathematically as well. So as announced, I'm going to talk about the landscape approach to wave localization. It's supposed to be a public lecture. I don't know how public it actually is. Can I ask if there are non-mathematicians in the audience? Anybody? No? Okay, cool. That makes it much easier. All right, so landscape approach to the wave localization. So first of all, let me introduce the problem the way it has been introduced to me, although we will go through many facets of it through the time of the lecture. Let's see if that actually works. Yes. Oh no. Let me see. I might have to stick to. Okay. So you're looking at the usual Laplace's equation, or rather equation for the eigenfunctions, eigenvalues of the Laplace's equation with, let's say, Dirichlet data on the boundary. The first thing we'll face in any partial differential equations course, or actually harmonic analysis course for that matter. If you are working on a square or a rectangle, a simple separation of variables shows you that the eigenfunctions are products of sines and cosines, and so they're uniformly distributed throughout the domain, as you more or less see over here. It so happens, however, that if the domain is more complicated than that, in particular here the white part is a part of the boundary of the domain, so this is the Dirichlet boundary, the eigenfunctions could localize, whatever that means, the way you can see it here. In other words, something stops the propagation of wave, and it gets confined in a very small portion of the original domain, although you can see no visible obstacles for it to get outside. And up to some moment, up to a very recent moment, there was no mathematical understanding of this phenomena aside from some very ad hoc results for dumbbell domains and things like this. In other words, why do vibrations localize? What features of the domain trigger localization? For what frequencies do they get localized? It could be that for one eigenvalue you have localization, and for the next one the eigenfunction more or less looks like this, uniformly distributed through the domain. And finally, how severely, in the sense that what do we even mean by vanishing outside of a very small set? We all understand that an analytic function cannot actually vanish per se. So what is localization? As I mentioned, this phenomenon in this form has received very little mathematical treatment up until recently, but that didn't stop physicists from making progress. And in particular, you can see this noise abatement wall. This is a real noise abatement wall on the highway around Paris, which has been built based on the empirical observation and physical understanding of the phenomenon of localization, actually from the exact domain on the previous slide. So this is that exact shape, localizing the acoustic waves here. And to this day, this wall holds the world record of the noise abatement performance, yet again without much of a mathematical theory behind it. Another example of localization, and perhaps actually a much more famous one in white circles, is the so-called Anderson localization by disorder. It's a localization of quantum states of electrons in a disordered material. Anderson got a Nobel Prize for it by now a long time ago in 1977, and back then alluded to indignity of the numerical simulations, which is still largely the case in handling the questions of the Anderson localization. Let me be a little bit more precise and also give you the idea of what the problem is about if you haven't seen it before. We are talking of the Schrödinger operator now, Laplacian plus V, and I mean, time independent, just a very basic Schrödinger. And the potential is some sort of a disordered potential. So one example that you can take is you take a square, you break it into many small pieces, you flip a coin, and you give the value 1 or 0 on those individual pieces. Here I have chosen this Bernoulli example, the Bernoulli potential, with 70% of 0, 30% of 1, with the idea that you would see that actually nothing stops the propagation per se. As far as the potential goes, there is a lot of light here, and that goes from corner to corner, so it's not clear why there would be any confinement of waves in the first place. And yet there is one. The eigenstates get localized, exponentially localized, so they are not cosines or sines. They are different in nature. These are exponents, as a matter of fact. And you can even see the log picture here. This is a periodic domain, so there is a period to it, but if you get infinite, it would be just exponentially decaying. Now, in principle, Anderson localization has received a lot of treatment, and the question of whether it is present and in which case it is present have been understood. In particular, while the most foundational results are perhaps due to Eisenman, Molchanov, and Froelich-Spencer in the beginning of 80s. In this Bernoulli case, it has been handled by Bourgain and Koenig in 2005, just recently, and some questions remain open. But most importantly, in all of these cases, what remains open are the questions pertaining to a particular potential. All right, there is a localization, in principle it exists, but what are the sizes, locations of the supports of the individual eigenfunctions? Can you identify where the first eigenfunction would be looking at this potential? This is probably the first one, but could you say it a priori? Where is the second? Where is the third one? What are the exact lines of the exponential drop? Because again, you can see that there are sort of lines. The exponential drop happens at some intervals across some contours. And finally, any sort of local information about the spectrum. Now, if you think that any of this is easy, or at least it looks like an easy equation, let me show you just briefly a filthy mess, according to Wolfgang Pauli, of semiconductors, which I signed by. It's still a filthy mess almost 100 years ago. This slide was intended more for physicists, and let me show you sort of a rundown of a mathematical problem. The problem with the semiconductors is that your potential is given by the eigenfunctions, and the eigenfunctions are given by the potential. The actual electric potential is borne by the charges themselves. So what happens is that you have your background Schrödinger equation with some, let's say, V0, think of it as periodic or random, and another part of the potential V, and this V itself satisfies the Poisson equation with the right-hand side given by eigenfunctions. So the potential is borne by eigenfunctions are borne by the potential, and all of this is an infinite system. Never mind the indignity of numerical computations. They take a month to complete. Every single computation in this business takes about a month, because it's an infinite system, because of the size of its billions of atoms and things like this. In reality, the situation is even more complicated, because you actually have disorder at all levels. So you are working with divergence form operator, you are working with the situation where boundary depends on eigenfunctions and effects like this. But one that I want to emphasize, which will probably speak to you even though this application might not, you need a local information, because semiconductor is based on the interaction of holes and electrons. So you need to know locally where are the holes and where are the electrons. The global information about the density of states or things like this is really completely useless. You really need to know how the supports overlap, how the electrons interact with holes. So this is yet another example, and here even theoretical understanding of whether the problem is well posed does not exist at this point. But nonetheless, it's safe to say that 50 years of study of the Anderson localization have brought beautiful results in both physics and mathematics, very powerful ones, and yet many of these open problems. Today I want to talk about something different. I want to talk about a different paradigm which gave birth to this particular project and which differs from any known approach to this kind of questions. When you look at the system, you see this disordered potential or irregular geometry or non-homogeneous material. When a wave looks at the system, it sees a hidden, complicated, but perfectly ordered landscape. And this landscape governs both the location of eigenfunctions and the eigenvalues that the system is allowed to take, the energies that the system is allowed to take. Given this huge variety of applications, of manifestations of localization, it's hard to imagine that such a landscape even exists. It seems too daring to assume so. And yet I claim it exists. It can be recovered numerically, mathematically, physically. And it can be used to predict the behavior of eigenfunctions, to predict the localization effects across all these different manifestations, to actually stop the light, to hide the sound, to be able to create the materials according to our dreams at the quantum level. But let's talk about the math side of it a little bit. So the story to me started by now about 10 years ago with something which seemed like a very straightforward, naive, and simple thought, and nonetheless turned out to sort of introduce just the right hero and to be immensely powerful in this subject. You take any positive operator, Schrödinger, Laplacian, multiplication by a matrix, any positive operator in the world. You look at its eigenfunctions, but instead of solving this infinite number, if you want, of eigenfunction equations, you solve one equation, HU equals 1, where H is your operator, so 1 on the right-hand side. It turns out that all eigenfunctions, all of them, are pointwise controlled by the energy times this solution U at all points. Think about it. They could look like sines and cosines. They could look like exponents. They are all over the place. It's hard to imagine that there is a uniform pointwise bound from above. And yet it is true, and this is what we will call the landscape. And to some extent what happens is that the places where this landscape is low perceived through many eigenfunctions is perceived by the eigenfunctions as sort of an artificial boundary which is hard to cross, because this is the cap which is restricting your motion as a wave. So here are a few first examples that we have done, again by now almost 10 years ago, which will give you some idea of what's going on. At the time I was working on the bi-Laplacian, Laplacian of Laplacian of U, so the first examples pertain to that operator. This is the Laplacian, this is the domain with a bottleneck, a crack, and a couple of points. Sort of think of small balls. And the same for the bi-Laplacian. The only smart reason behind the choice of the domain is sort of to introduce all singularities I could think of at the time. For the Laplacian, you solve the landscape equation, Laplace equals 1 on this domain. You have one value and a separation into two subregions, if you sort of think of it as a mountain landscape. For the bi-Laplace, it's a very different result. You have about 5 values and 4 subregions. So the result is very, very different. Let's see if the eigenfunctions respect it. So again, in red are values of the landscape. Here are the results for the eigenfunctions. For the Laplacian, they are indeed exactly in the 2 regions predicted by the landscape. For the bi-Laplacian, they are indeed in the 4 regions predicted by the landscape, with one exception over here, which we will discuss later on. This is also explained by the landscape mathematically. But the point is that there is a definite correspondence already at this naive level. Since then, these results have been confirmed experimentally on duraluminum plates, and by now are actually part of engineering constructions. Physicists move faster than we do. So this has been published in PRL a couple of times in theoretical and experimental level. But let me shoot through another example, which is much more recent and which pertains to the different equation, as a matter of fact, system of elliptic equations. This time corresponding to the describing actually the enzymatic activity, the catalytic proficiency of enzymes. The point is that when you look at the enzymes, there is a very complicated molecular scaffolding going on, and so they look more or less like this. And there are hotspots which are responsible, the thread scene, which are responsible for the actual enzymatic proficiency of which basically accentuate the properties by a factor of about 20. The landscape predicts these hotspots with the precision of 2 angstrom, which is basically either getting it on the point or pinpointing the next molecule. Again, forget the bi-Laplacian, forget the Laplacian, forget the vibrating membranes. This is at the molecular level. You are looking at the molecules, and you are pinpointing the exact location of the hotspots, again, with the precision of 2 angstrom. This is a complete total magic at this level of scales. But since I started with it, let's talk about again about the Anderson localization effects. And now that we have so this is a new disordered potential, now somewhat more complicated than just 0, 1, although I'll get back to Bernoulli soon. The idea is, once again, you are looking at the landscape, at the solution to LU equals 1 instead of the eigenfunctions themselves. You take the picture of the values, however you define the values, just think in the philosophical way, but there are precise definitions behind it. And the claim is that those should, to some extent, describe the location of the eigenfunctions for you. So as promised, I actually prefer the Bernoulli example, not the original example, for the reason that to me, it's much more mesmerizing, because you actually cannot believe that there is any localization here. It should, in principle, be completely propagating. Look at this, tell me if you see any localization, if you can imagine where the localized eigenfunctions would sit. I personally couldn't at the time, at least. This is the landscape picture. This is the values of the landscape. Let's see if they indeed predict the location of the eigenfunctions. This is the first one, exactly in the values of the landscape. This is the second eigenfunction, repeating it even with shapes. Third, fourth. I have a movie here, but it's a pretty boring movie. It sort of goes all over for a very, very long time. But the point is that there is an immense precision in this prediction. And once you see it, you sort of get greedy, and you think, but wait, Anderson localization is about exponential decay. This eigenfunction, or any of the eigenfunctions I showed you, in fact, secretly decays exponentially. You know, at the linear scale, you see a bump, and otherwise 0. At the true scale, at the logarithmic scale, you see that this is not 0, but exponential drop. What you also see at the logarithmic scale, this is gradient of the log, is that exponential drop doesn't happen uniformly. It's not e to minus x. Exponential drop happens in these red areas, which are, well, maxima of grad of log, hotspots of the grad of log. So your eigenfunction is uniform drop, uniform drop, uniform drop. This drop happens across some curves. Imagine our surprise when we superimposed on this picture the values of the landscape U and saw this immense precision. The values not only give the region at the linear scale, they describe for you the rate of the exponential decay down to 10 to minus 20. This cannot possibly be a pointwise control. Again, we are at 10 to minus 20. There is nothing pointwise here anymore. And yet there is this immense precision. This is a bigger picture just so that you believe that I don't cheat on the size of the picture. There is really an astonishing precision. So what's going on? Well, it turns out that yet again the same hero, and there will be a reappearance of it at many, many levels, by a completely different phenomenon, controls the exponential decay of solutions to the Schrödinger equation. So what happens is that you can rewrite the initial equation, sort of conjugating it in a smart way, as another equation with the same eigenfunctions, with the same eigenvalues, where the potential is now 1 over u, 1 over the landscape u, instead of v. And then there is a non-trivial divergence term, but basically, you know, this is homogeneous to Laplacian. So there is some depth there, but for now you can pretend that it's the Laplacian itself. So the point is that in place of the potential v, you could as well think of the potential 1 over u, where u is the landscape. And the very important feature of the landscape is that it's structured, where u has this random crazy pattern of buildings and, you know, huge zero areas and things like this. The landscape prescribes for you a very clear, I mean, it doesn't look super clear, but it's really much more structured picture of wells and walls, which now hold the eigenfunctions. And this is the 3D picture, so you have a very clear idea of where are the chambers where the eigenfunctions are allowed to sit and how they would redistribute. Okay, now that you've seen enough fun pictures, theorem, buckle up. You take an elliptic operator in divergence form, dy grad, with a bounded measurable coefficient a, plus potential v, again bounded measurable potential. On a Lipschitz domain, or you could take non-tangentially accessible domain, or even more general than that. Let's pretend Lipschitz for the sake of the conversation. The localization here could be coming from A, from V, from boundary, from all of the above in a fancy mix. Solve while u equals 1 with the same boundary conditions. Take this landscape u, take the reciprocal, 1 over u. This is an example of picture in 1D of what you are looking at when you take the reciprocal. And now this 1 over u, this mapping of 1 over u, gives you the manifold as perceived by the eigenfunction, in the sense that you cut at the level of energy lambda that you are interested in. And the wells which are below this level are going to indicate for you where the eigenfunctions are allowed to be localized. And the walls, the thick, huge walls between the wells, are going to prescribe the exponential decay according to the distance induced by 1 over u. So the eigenfunction is, roughly speaking, exponent to minus rho 1 over u, where rho is the distance induced by 1 over u on this manifold. So it costs you exponentially to make every step, whether you are going up or you are just going in the distance. So both the height and the distance of the size of the wall actually matter, and somewhat more generally for general equations. So this indeed describes to you why the exponential decay you see is governed by 1 over u, as I showed on the previous slide. This furthermore gives a chance to prove certain projection estimates, and what I mean by this is a diagonalization, or as physicists say, decoupling, in the sense that you can prove that the eigenfunctions of your initial system are actually the eigenfunctions of these tiny regions, the node sort of depicted by the landscape, delimited by the landscape, modulo exponentially small errors, and conversely, every eigenfunction of the small region corresponds to some eigenfunction of the initial system, modulo exponentially small errors. Same for eigenvalues, same for the eigenvalue count. In other words, your system is basically exponentially decoupled. And knowing the information about the spectrum of individual subregions, you have information about the spectrum of the big system to start with. A quick note, which to me as a harmonic analyst particularly speaks as to power of the landscape, but you might or might not, it might or might not be closer to you than the previous theorem. What basically goes on in my personal view is a certain precision of the uncertainty principle. So what I mean by this is that the reason why the eigenfunction does not go through these tiny openings of the initial potential is that it's fat. It has a kinetic energy. You know, where particle could go is not where wave could go, which is what all of the quantum physics postulates. So the eigenfunction has kinetic and potential energy, and the job of the uncertainty principle and the value of the uncertainty principle is to sort of sum up effectively the contribution of both. This is really what 1 over u does. Because by this conjugated rewriting, you are getting into a certain reduced kinetic energy, which is really, really tiny, and the effective potential energy, which takes up almost all of the information. That's why 1 over u is so better structured and carries so much more information than v. So in particular, in the example with the Dirichlet problem, which corresponds to an infinite quantum well, you don't have any potential. You have localization coming from, well, the actual boundary. 100% of energy is kinetic, so you have 100% here, 0 here, versus if you rewrite it using the landscape, you get 96% here and 4 here. So really the potential energy, the information, is completely encoded in 1 over u. And you can, sort of in the last theorem, I will show today, this information is propagated into theorems and the count of eigenvalues and things like this. This is really not just words. But for now, so this gives you transport and other things that you probably don't care about, but people who build semiconductors do. But let's play a game, which Doug has called Where is Waldo? Doug Arnold, which some of you might know from the University of Minnesota. And this is a game of eigenfunction prediction. Let's say we are looking back at the Schrödinger equation Laplacian plus v. This is your potential v for the time being, random, 1D. Here is a question. Can you, looking at this potential, predict where would be the first eigenfunction? Anyone? Come on, play a game. So the idea is that, it's typically where potential is low, but also where the low place is wide. What matters is sort of having a thick and simultaneously profound well. Problem is the correspondence of how thick and how profound it is very difficult to estimate by naked eye in the examples like this. So here it's virtually impossible. I can tell you that never ever anybody guessed where the first eigenfunction was. So I know I'm going to win when I'm starting the game. But let's say we now look at the 1 over u. So we solve the landscape equation. We take the reciprocal. We look at the effective potential 1 over u. It has a somewhat different, it looks somewhat differently. It's still pretty disordered. But the point is that I can actually pinpoint the lowest well, the next well, the next well, the next well, and so on. So I'm doing that. I'm marking the wells in the order of their appearance and the order of how deep they are. I'm marking the width of the corresponding wells. So this is all from the landscape. And I'm pretending that this is my prediction of the eigenfunctions. So 1, 2, 3, 4. For now, it's information just from the landscape. Well, guess what? First eigenfunction, second, third, fourth. Exactly where promised. So not only you can say that this bunch of 100 regions contains the first 100 eigenfunctions, you can say in which order they come. Now you know the rules of the game. Let's try again. How about this potential? Well, this is a tricky question. This is the same potential times 64. The only thing I changed is the height of it. Would the answer be any different? Well, the change to the landscape is nonlinear. It's not like multiplying potential by 64. You multiply the landscape by 64. There is that Laplacian term hanging in. And actually, the landscape now looks very, very different. This is 1 over u in this new world. The first 4 wells in very different places with very different widths. And guess what? The first 4 eigenfunctions, 1, 2, 3, 4. Exactly on the point. So you're really prescribing them in the absolute perfect order. You could tell me, you know, this is 1D, life is easy in 1D, I can solve an ordinary differential equation, although not really, but let's pretend. How about higher dimensions? Well, this is a 2D case. 1, 2, 3, 4 deepest wells of 1 over u, 1, 2, 3, 4 eigenfunctions. The exact place and the exact order, the exact shape, everything just predicted from the landscape. You could go further from it, but it turns out that there is this magical relationship, that there is a constant, dimensional constant, independent of the potential, whether it's random, not random, periodic, crazy, Bernoulli, Anderson, whatever you want. There is a dimensional constant, 1 plus n over 4, such that the eigenvalues are virtually equal. For now, I'm only speaking of numerics. I'll show you theorems later. Virtually equal to minima of 1 over u. So the reason why the deepest corresponds to the first and the second corresponds to the second and so on is actually more miraculous than that. You can recover the values of the eigenvalues from the minima of the landscape. Again, modulo a constant which does not even depend on the potential. Same with locations, also with astonishing precision. Let's see a bigger scale computation so that you don't think that it's only about 4. So this is an 80 by 80 grid in 2D, the one I showed you from the beginning, Bernoulli case. A random potential. First 100 minima of 1 over u, there are about 100 total, so this is virtually all minima of 1 over u in blue. First 100 eigenvalues, minima in green, eigenvalues in blue. This is the ratio. Virtually on the point. And by the way, 1.5 is 1 plus 2 over 4, as promised. Another example, a very different potential. This is a severely correlated potential. Those of you who do any sort of probabilistic games know that this matters. This is the one coming from cold atoms. Very different picture of the spectrum. Eigenvalues in blue, minima in green. This is the ratio. So both patterns here are different. The ratio is still 1.5. This is a histogram of about 10 to the 6 eigenvalues. This is 1D because that's what made the computations possible, but just to give you an idea that it's really very sustainable in large measures. But now you would tell me, how can this possibly persist? And you would be right, because there are fewer minima than there are eigenvalues. You know, in a finite domain, there is a finite number of minima and infinite number of eigenvalues. In an infinite domain, something like this still happens. So minima naturally describe the bottom of the spectrum. You cannot do better than that. It turns out that the landscape, nonetheless, still can describe it all, but yet different phenomena. 5th or whatever, 6 different phenomena using the landscape. So as most of us know in mathematics, and certainly virtually everybody knows in quantum physics, one way to be able to talk about that, to give some rough estimate on the eigenvalues, is to use the Weyl law. So the Weyl law tells you that the number of eigenvalues below the level mu, so n of mu is how many eigenvalues you have below mu, is give or take the volume in the phase space of xi squared plus v less or equal than mu. This is a very rough estimate. You will find almost no precise proofs of it, to be completely honest, for general potentials, because it so much depends on the features of v. But it's true asymptotically. So this is true as mu goes to infinity. Problem is at the bottom of the spectrum, it's totally useless. Or actually up until lambda hits infinity, whatever infinity means. So here you see this random potential V. In blue is the true density of states, the true curve of n of mu. In green is the Weyl's Weyl law. So asymptotically it corresponds to the blue, but it's pretty desperate down in the bottom. In red is the curve of the Weyl law using 1 over u instead of v. So I guess no advertisement needed. Another example is the Bernoulli potential. The Weyl's Weyl law, the original Weyl law, basically gives you two curves. You can imagine why, because up until you hit 1, this volume is the exact same, so this is it. And then once you have hit 1, you basically behave like the Laplacian, and this is your new curve, and it asymptotically happily matches the true one. Problem is, again, it has nothing to do with the actual disordered effects. In red is the Weyl law using the landscape 1 over u. Here it is. It's true from day 1, from the bottom. Yet another example, if you think that this is all about the random case, is the periodic potential. The curve of the true Weyl law is the exact same as for Bernoulli, because again, all it cares about is how much of white or blue you have up until some level. So this curve is the exact same. The landscape, nonetheless, is again precise. Modulo not catching the spectrum gap here, but definitely precise in the beginning. So what's going on? Well, this Weyl law story, actually this Weyl law story more so, and the count of the minima has been, we found it about 2-3 years ago by now. In about a year, it made it to engineering textbooks. In about 2 years, it was used for the actual devices, none of which, has given any sort of idea of what to do mathematically. I mean, this is really the phenomenon that has never been seen before. And now, finally, I can say that there is a theorem, although no engineer cares that there is, but it gives me personal satisfaction, which addresses it. So here is what's going on. First of all, you are looking at the data. You are looking at this precision of the minima at the bottom of the spectrum. You are looking at this new Weyl law throughout the spectrum. The problem is that neither of this can be the ground truth. When you are trying to prove a theorem about it, you realize perfectly that you can fake the counterexamples. Fake meaning they would not be generic, but you definitely can find a counterexample to that. So it was not clear even what to conjecture. Eventually, this is the result. You take the Schrödinger equation. I didn't go further than that yet. Solve for the landscape. And what you actually should be counting is the number of cubes which contain low minima. So you take a certain scale lambda, up until you are going to count, so lambda is the threshold. You are taking the tiling by the cubes of size lambda to -1/2. I won't go into details because of the timing of how you separate into cubes and so on, but this is sort of the right scale. And you look how many cubes have minima below lambda. And this estimate gives you the constants, which are basically dimensional constants, independent on the potential, independent on anything, on the size of the potential, on whether it's random, whether it's periodic, smooth, non-smooth, any other features. So uniform dimensional constants, such that this estimate holds from above and below with the corresponding constants. At this point, I have it with 2 possible preconditions, but it's sort of, it depends on the circumstances what the proof actually needs. It holds if one u is doubling, if the, roughly speaking, average of u on a cube is proportional to the average on 2 cubes. Those of you who like weights, this means that it's a doubling weight. Which, for example, is true when v decays faster than squarely at infinity, or if v is periodic, or in many other circumstances. Or, and this pertains to Anderson potentials, if minima of 1 over u grow exponentially at the bottom, so that exponential takeoff is also what's sufficient. Now, sadly, this is not proved yet mathematically. I do believe it's true. It's certainly true numerically. I do believe we are pretty close with Guy David actually on proving this, but I won't announce it just yet to be safe. So at this point, this is numerical, but I believe it's actually a mathematical statement. And in that case, you have this perfect count throughout the spectrum. So notice nothing is asymptotic here. This is the first non-asymptotic result in this business. While pertain to lambda equals infinity, there are semi-classical results which pertain to lambda going to 0. This is the first non-asymptotic result. Independently of lambda, you have an approximation of the spectrum by nu, and this is exactly what sort of matters in all these pictures. So again, take the cube, chop into sort of tile the space into the grid of size lambda to -1/2, count on how many you have minima below lambda, that gives you your sin. It corresponds to, so first of all, notice that if you had a regional V, you would not be able to play this game. If you have a Bernoulli potential in all cubes, the minimum would be 0, so it would be completely useless. In more general case, not necessarily, but still completely useless. If you have a geometric information, again, minimum of V is just 0, so completely useless. And this actually always works. So this incorporates both the approximation with minima and what we call new Weyl law, meaning the approximation with the volume and phase space in one package. Basically what's going on is that this is a count of how many cubes you have with very low minima. Up until some moment when your lambda is very, very low, there is one minima per cube. So counting cubes is the same as counting minima. This is why there is this one-to-one correspondence. And then when you exceed the total number of minima, basically you start counting sort of more the volume and the phase space of 1/u style. But again, the point is that it holds throughout the spectrum. I already alluded to the fact that it's not asymptotic. Constants don't depend on lambda. In bad news, well, sorry. One, the constants are actually necessary for obvious reasons. And two, it's still incomplete in the Anderson case. Again, for the point that I said, you need to prove that the minima take off exponentially. This is a very qualitative information. I basically need a certain integral to converge, which doesn't converge yet. Or at least I don't know why. So I'm hopeful, but this yet needs to be finished. But let me give you yet another example of how beautifully it works, which is sort of simple and illustrative at the same time. So you take a particular Schrödinger equation. This is actually a challenge from Eric Ackermann, a theoretical physicist in Technion. But it's also a known example mathematically. You take Schrödinger with the particular potential, which is k being a constant divided by x squared. If you haven't seen it before, it's a completely magical guy in the sense that whether or not your spectrum is bounded from below depends on the value of k. So notice that this is sort of borderline positive, not positive operator, meaning that Laplacian is positive, this is a negative term. So the question is who wins? Whether Laplacian wins over this term or the other way around. It's very well known that when your power is different here, so when the potential is slower or faster, it's very easy to prove who wins. If potential is slower, it's Laplacian, and if the potential is faster, then the other way around. It's absolutely magical that the constant matters here. The constant is known to physicists for a certain homogeneity considerations for the eigenfunctions themselves. But it has never been possible to actually compute it mathematically, to prove it mathematically, that this is the threshold. And the landscape, well, sort of does the job very easily in the sense that quite magically, unlike the eigenvalue equation, the landscape equation can be solved here explicitly. You know, it gets into an ODE. Everything depends only on R here. I mean, you are in spherical invariant system. You write this in spherical coordinates. This is 1/r². You just solve it explicitly. The particular solution is not pretty or interesting, but the point is that it shows you the critical constant on the point. So the fact that this first threshold is given by the landscape is absolutely explicit in this context. And this further, you know, again, I'm going to shuffle through this very fast. This applies to all these crazy semiconductor systems. You get to shoot through with the landscape equation instead of solving this infinite system in which, again, potential depends on eigenfunctions depend on the potential, which could take a month. You shoot through with the landscape equation. It makes it 1,000 times faster. I'm not exaggerating, 10 to the power 3. So the computation which used to take a month now takes a day and actually makes it possible to use it for predicting the behavior of semiconductors. Local density of states, electrons, holes, absorption, emission, recombination. I understand I'm just saying words, but sort of everything you want to know about the semiconductor from here. It's absolutely magical that you are actually looking at overlaps, because there is a landscape of electrons, landscape of holes, and what you care about is how the two of them overlap to give all of those coefficients. Shooting through this, and sort of the end of it. So at this point, the project has grown beyond my wildest expectations, or perhaps even desires. It is, as Volodya has pointed out, a so-called Simon's collaboration in mathematical and physical sciences. We have been awarded it this summer. There is one or two per year. This is the collaboration network that you can see over here. So just quickly, most of the results I have showed you are with people from here or will be with them. This is myself, so Marcel Filoche is one of the main physicists on the project. He's in École Polytechnique. On the math side, people you probably know, Yves Meyer in uncertainty principle, Guy David, harmonic analysis, and geometric measure theory, which are sort of hidden under the carpet here, but those boundaries of landscape regions are rectifiable and you have to deal with it, and not better than that. David Jerrison at MIT, both in PDEs and harmonic analysis. Doug Arnold at Minnesota is the main computational person, so all the beautiful pictures you've seen have been done by Doug. And on the physics side, Claude Weisbush and Jim Speck in non-organic semiconductors, Alana Spe in Institut d'Optique in cold atoms, and Richard Friend, Sir Richard Friend, actually here in Cambridge. Unfortunately, he's not around today. But he's the main collaborator on the organic semiconductor side. And in particular, we will have actually a meeting here in Cambridge in October devoted to organic semiconductors. If you are curious to know more, it's at waveview.edu. I didn't mention the consultants, but you probably know Jill and Terry Tao, and Nakamura is the Nobel Prize winner in blue LEDs in non-organic semiconductors, collaborating on this as well. Okay, I'll finish here as promised yesterday, exactly at 4:50. So thank you very much.
Thank you, Svitlana, for a nice talk. Now, questions, comments, and remarks. Boris?
May I ask about the smoothness of this landscape solution? Do you know something? Or?
It's formally C infinity just because you have solved the Laplace U plus VU equals 1, so there are interior regularity results. Or C1 alpha if V
norm estimate, I mean in some classical.
In the Sobolev spaces, no. I mean, quantifiably, I mean, in terms of the qualitative results, again, it's sort of whatever interior regularity gives you. In terms of the norms that you care about mostly, and actually so do I, no, we don't have those results, and they must be pertaining to the systems in the sense that you take the particular class of potentials, you have a particular class of smoothness results, something like that. So
the number of minima depends on the norm.
Very good point. I would love to know that. I don't know that. I mean, as a matter of fact, the state of the art now is that we have this very precise understanding of how features of the landscape imply features of the system of the eigenfunctions. But we have still very little idea of how the initial system implies features of the landscape. So yes, I'm with you. I want to know that too. It's basically what we are working on right now. Very good question. Yeah.
Other questions? I have a question.
Mm-hmm.
Maybe just maybe very kind of simple question to you. So as we learned from your talk, this landscape function plays a very important role. But landscape function is obtained from the equation, the operator applied, and on the right-hand side you have 1. Could you explain on kind of intuitive level what is so important about this 1? For instance, if I replace that 1 by some other function, I will get some kind of other landscape, or what?
Another very good question. So I can tell you that where we started from, where the initial idea came from, it was intuitively sort of the deflection of a plate under a uniform load, in the sense that when you think about the vibrations, like actual vibrations, mechanical vibrations, as opposed to quantum waves, what one stands for is you take your membrane, you apply one uniformly to the entire thing, and you take a picture of sort of the shape that you are getting out of this. And the places where the system is stiffer, you see them this way, and the places which give out more are the places where the vibration is going to happen. So in some intuitive level, that's what one stands for. So this is a posteriori explanation on mechanical level. In the mathematical level, honestly, the thing that happened is playing with the equations and integration by parts, and we got this first result, and that's how one appeared. I integrated the green function, and suddenly, ta-da. So it was a complete magical, actual manipulation of the equations. In the context of quantum systems, to this date, I don't know, in the sense that it's sort of a magical mathematical tool like a black box, which transfers for you the information about, sort of from the information about the system to the information about the spectrum. It's like the Fourier transform for non-disordered systems gets you from the physical space to the phase space. This is sort of, and then oscillatory integrals, Fourier transform works for pseudo-differential operators. This is sort of the guy, if you want the Fourier transform analog, which actually gets you from the physical space to the phase space to the spectrum for systems which are inherently more complex or disordered. But you are absolutely right that this translation is kind of a mathematical mechanism. And every time I talk to a quantum physicist, who is one? I mean, I don't know who is one. And I think that the moment we learn, we are going to learn actually much more about this.
Other questions? Oh, Doug? Yeah.
So you mentioned about the biharmonic equation. So is there something fundamentally different between Laplacian and the biharmonic operator, and indeed other operators?
It's much more sensitive to point irregularities. So at a very naive level, the point, for example, in 2D, if you take one point, it's not even seen by harmonic functions. And by the biharmonic functions, it's actually seen. So if you clamp a nail, our first example, which I never showed here, is that if you take a rectangular bench, like literally rectangle, and you clamp one nail on a strategically chosen point of this bench, if you do it for the Laplacian, mathematically, you would get the same sines and cosines. If you pretend it to be a small circle, you might actually see it acknowledged, but sort of it won't change much. You will just have a big there. For the bi-Laplacian, this one nail, if you choose it strategically, basically prevents the propagation of waves for the first 200 of frequencies. So you take a bench, you stick a nail, and you can jump here as much as you want, and the person sitting next to you would not feel the vibration at all. And this is already used in engineering constructions. And to this date, I don't know why. Landscape sort of describes it, but yet again, it's a tool, it's not an inherent definition. But that's the thing. So basically, the bi-Laplacian describes the vibration of rigid plates like iron, or the coverings of airplanes, the coverings of ships, the plaster walls. Yours are not plaster, but those things. So it's a rigid clamped plate, and the rigidity is the word. So it's more responsive to the boundary, to small boundary irregularities than the Laplace's equation is. It's more rigid.
So you allude to quite a lot of numerics that's sort of going on in the background here. So I was wondering if you could comment a little bit on that. So one of the big problems typically in spectral computations is to even just get convergence and also have any kind of error control on what's going on. So could you comment a little bit on that?
It's a very, very, indeed, it's a very difficult issue, and you could have noticed that numerics here is actually somewhat restricted in sizes and everything. Honestly, the right person to ask is Doug Arnold, who is actually doing them. My understanding is that indeed the problem you are voicing is very relevant. We are trying to stick to either 1D, in which case you can handle things somewhat more directly, or in 2D it's 80 by 80 potential. I think he gets about 10 points on the mesh, so that's 10 times 800 by 800. Yeah, that's a pretty sizable computation. So in short, you would have to talk to him about the particular methods and error control, and we have a science paper where he details it somehow. But it's indeed a very relevant problem, in particular for 3D computations that we are facing right now. Because in 3D, it's just excruciatingly bad. And that's why the landscape is so much more useful. So the trick is, in the early days of giving this talk, people would ask me, but wait, computing the landscape is sort of the same because you have to invert the matrix. We don't do that. It's a very sparse matrix because there are a lot of zeros in it. I mean, if you write the Laplace as a matrix. And we are actually honestly solving, HU equals 1 by sort of row and column operations, instead of inverting the matrix, which would indeed cost a lot. So I can only tell you that in these semiconductor computations, because physicists cared so much about them, as I said, it's about 1,000 times gain in the speed of computation if you do the landscape instead. In enzyme computations, I think we gained about 100 times faster with landscape than with the actual eigenfunctions. Another thing that we can do that we are exploring right now is that it gives you a good initial guess. So even if you want the true eigenfunctions and not the mock-up using the landscape, this gives you a very good initial point to start from. You are sort of computing the landscape once, and you have the initial guess for your eigenfunctions, which then can be, can converge much, much faster. But this is sort of words, and beyond words, you would have to ask Doug, because I'm not an expert on that part of it. But the idea is, yes, it's a very powerful method to basically get you started, and we are using it.
Other questions? If not, let us thank Svitlana again.